All right, so let's talk about linear regression. Linear regression. So just a disclaimer, um, we are going to cover linear regression again in week 3 in its blue glory, right? So what I'm going to do here is a very watered down version. And in fact, even in week 3, we're going to do quite a watered down version because if you want to look at the literature of regression problems, uh, there is a whole module on just regression problems, right? And you could probably take those modules in the mathematics department, right? But here we're just going to go through a watered down version of a watered down version, all right? Okay, so recall back to say your science labs, right? In your science lab, you are perhaps what you have already did is you spin some pendulums and you record the number, the time it takes for the pendulums to swing the whole. I don't know, man. Why would you do that? But okay, let's say you did that, right? What you have is going to be some data points, right? You collect some data points from the experiments, and after you collect these data points, right? What you need to do is to draw a best fit line through this data point, right? So perhaps this is a nice best fit line through the data point. Now, for this particular problem, we can actually frame it as an optimization problem, right? We want to choose a particular line that actually gives you the best fit to the data that you have. Okay, so if you want to frame this as an optimization problem, then we have to do two things. We have to decide what the parameters are, and we have to choose a good objective function to optimize over, right? So it's similar to the area problem that we have previously. So for the parameters, it's essentially asking you, what can you change in this problem? Well, the thing that you can change in this problem is the line that you decide to draw. So it is very possible that you decide to draw this red line instead of the green line. It is also very possible for you to draw this blue line instead of the green or the red line, right? So how do you define each of the line uniquely? Well, if you recall back to, say, one of the mathematics course that you've taken previously, um, you only need two parameters really, right? You only need the gradient of each of the line. Uh, Let me rewrite this. You only need the gradient of each of the line, which is m, and you need the y-intercept of each of the line, right? Which is c, right? You only need these two parameters. So given a particular m and c, you can actually see that it reflects as a line on this graph, right? Cool. So now that we identify the parameters, we have to decide how to determine if one line is better than the other line, right? So if you look at this an example, you can roughly see that, well, the green line is better. This green line is better than this blue line for sure, and it's better than this red line for sure. But why, right? Why is this the case? So I'm going to propose an objective function that kind of makes that. Okay. So what I'm going to say is that I'm going to look at the distance between each of the data point to the line that I draw. Right. So you can see all the blue things that I've just drawn. This is the each of the distance from data point to the line. And you can see that this distance is quite large, right? As compared to, say, the green line. If we do it for the green line, let's do it now. If we do it for the green line, we have this, 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 and this, right? So it's actually, if you think about it intuitively, this is actually a smaller quantity, a smaller distance away from the point, right? So intuitively, it seems like, yeah, this measure is good. It tells you how far away each of the line is away from all the data points, right? And this is exactly the objective function we're going to use in this case, right? So let us think about what is this length first, right? Let's talk about just one data point first. What is this length? I'm going to define some notations first. I'm going to call each of the data point x1, y1. The second point will be called x2, y2, and so on and so forth, right? All the way up to this point, which is x superscript 5, y superscript 5. And really, this distance over here is essentially the y value of this, the difference between y value of this and this, right? So what is this value, right? So this particular value here, we know this is essentially just y1. And this particular value, we also know, right? If we know m and c for this particular blue line, then we know that this point is essentially mx1 plus c, right? Now, what we all have to do is to make sure that this can never become negative. So one trick that we can do is just square this thing. So what we have now is the square distance between the point and the line itself. And we just repeat it for all the points, right? So for one point, the distance is essentially yi minus mxi plus c square. And we just naively sum over all the points, I equals to 1 up to 5. Okay, so as you can see, when you collect the data, your data become the constants, right? So these are essentially constants in the problem. Your y's, i's, and the xi's, they're all constants. What change is the parameter, right? So you can choose a different line, which will result in a different MMC. And by choosing a different MMC, what you essentially did is to change the value of this objective function, which I'm going to call it L now, right? So you can see that this objective function is parameterized by just two parameters, m and c. And given a choice of n and c, you get a different objective function. You get a different value for this objective function. All right, so let us now try to solve for the objective function. Right, recall that our objective function, parameterized by m and c, is the summation of I equals to 1 to 5 of y superscript I minus m x superscript I plus c squared. Okay, how do we do this? Well, in order for us to try to find the minimum point of this particular function, what we need to do is to find the partial derivative of this objective function with respect to m and respect to c, and set both of them to 0, right? What we need to do is set both of them to 0. Well, but before we set both of them to 0, what we need to do is to try to find out what the partial derivative actually is. But this is actually quite easy, right? So in case you have forgot how to do partial derivative, essentially you set every other things as a constant, other than the things that you are differentiating with respect to. In this case, is m. And then you just do it normally, right? So in the summand, what you have is apply chain rules. So you have 2 y superscript I minus mx superscript I plus c. And then you differentiate whatever is inside this bracket because you apply chain rule, and that will give you negative x superscript I, right? And then you just have to sum, bring back the sum from I equals 1 to 5, and you're done. So similarly for this, let's bring back the sum. You have 2 y superscript I minus mx superscript I plus the c times negative 1. Okay, and then you set this to 0. So at this point, you realize that this is essentially a systems of linear equation, right? You're trying to you have a few equations, but all of them you want to set it to 0. So what is the field of mathematics that is helpful for you to solve this problem? So it turns out that if you think about it, It's just linear algebra, right? And this is where linear algebra pops up from the picture. In this video, I would not describe how we can express this in terms of in a matrix multiplication form, but you should be able to do that if you think about it a little bit, right? And go recap your linear algebra basics. And hopefully you can try to do that on your own and solve for these systems of linear equation. But what I want to discuss now is something that's slightly different. So think about cases where the objective function is not as straightforward, right? Where you're not just choosing a line. So this particular portion right here, the mx plus c portion, could be super complicated, right? It could be a super complicated function that perhaps you know how to find a derivative, but it is quite impossible for you to express it in terms of a matrix multiplication form. So in those cases, you will learn in, again, around week 3 or 4, that there is algorithms for you to try to approximate what is a good minimum point of this loss function L, right? And if you have been following and reading out a little bit on machine learning, this algorithm is called gradient descent. I will not go through gradient descent here either because it's going to be reinventing the wheel of what is going to happen in a few weeks' time. But it's just something that you can watch out for, right? What I will do now is, in fact, to show you how probability pops out of this picture, right? Nothing is intrinsically probabilistic so far. So how am I going to do it? You see,